Morning, everybody. Sorry I'm not going to be there again today, so rather than having you watch a video from someone else, I figured I'd throw together a quick little video for the notes that I had planned on doing with you guys today. So yesterday you watched a video, hopefully it worked for you. I know Mrs. Sample emailed me saying that some of you had some issues with the video, so hopefully today goes better. But in the video you watched a guy go through just some examples of how we would solve exponential equations, which is what we're diving into a little deeper today. So I wanted to start first and foremost with just some definitions. So up here in box one, I do want you to try and follow along. I don't have one pre-printed for you, so you can just do kind of old school regular 4-box notes. Take a piece of paper, fold it in fours, and make each box. So if you need to pause the video for a second and grab a piece of paper and get yourself situated, then go ahead and do so. Once you're ready, then click play and listen to me ramble for a little bit. All right, so in box one, we're doing exponential equations. So again, this is kind of our definitions vocabulary box. So an exponential equation we know is an equation, shocker, it's an equation with, let me zoom out a little bit and situate this, there we go, with variable expressions as exponents. So very similar to our exponential functions that we saw before, where that x value is in my exponent. Here just a little more broad. It's just an equation that at some point in that equation, or at least in one spot in the equation, one or both sides of my equations have an exponent that is a variable. So a little more generic today, not so function notation wise, just more of here's this equation that are equal to each other, let's just handle it. So we've got something called the property of equality. So there's a lot of different kind of ways that we can interpret the property of equality, specifically with exponential equations. I'm going to kind of break this down into 3 different levels to give you the definition first based on the wording of it, the actual definition of it for properties of equality, and then I'll give you the algebraic and then kind of an example with some numbers in there. So we'll kind of pare it down a little bit and hopefully it makes more sense. So what the property actually says in words is that if 2 expressions with the same positive base b are equal to each other, their exponents must also be equal. So what that means, algebraically, if I was going to write this out, this gets a little complicated, and that's where the number example will hopefully make a little bit more sense. Algebraically, we have that if b is bigger than 0, so it can't be 0, and it can't be 1, those are my 2 requirements for my base in an exponential function. So the same requirement, as long as my base isn't negative or 1, that then b to the x power equals b to the y power if and only if, and I'll remind you of that, if and only if x equals y. So that IFF, that's an abbreviation that you'll get used to, especially, at least there's a couple of you in geometry right now as well. So you probably have seen Mr. George use that in proofs or conditional statements, if-then statements. If not, or if he hasn't gotten to those yet, or those who are taking geometry next year, get used to seeing that. He does use those from time to time. If and only if is just that. That's what IFF stands for. This is true if and only if this other thing is true. So in this case, b to the x power equals b to the y power if and only if my x value and my y value are equivalent to each other. Because if we're on the same base, the only way that that's true is if those 2 variables are the exact same value. So what that looks like with an actual example, doing a conditional statement again, if we have 2 to the x power equal to 2 to the 5th power, the only way that that's true is if x equals positive 5. So here again, we have my two bases that are the same number. I know they're set equal to each other, so the only way that that's true is if that x value is equal to 5. And that's what we're going to be working with here. So for the first set of problems we'll do over here in box 2, we have what we call like bases. So the numbers that are the base of my equation on both sides are already equal to each other. They're the same number. So if that's the case, then we know that their exponents have to be equal to each other. So in this case, 3 to the x plus 1 power equals 3 to the 5th power is only true if we have x plus 1 equal to 5. I'm just going to set those two exponents equal to each other. And now that becomes a problem that we did early in chapter 1. I'm just going to use my inverse operations to solve for x. 4 is my answer here. Positive 4. Now we should, I'm going to do this with this first one just so you guys get a look at what it, get a feel for what it looks like. We should be checking our answers, and this should work. I mean, obviously, how we check our answers with everything else, we're just going to plug that solution that we think my x value is equivalent to into my equation. So here we get 3 to the 5th power equals 3 to the 5th power, which is, what, 243, I think? Oops. 243. Right, because 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 would be, 243. So it works, so we're good. Now, we should be doing that anytime you have the time to, especially when it comes to a quiz, which, we don't have another one this chapter, so once it comes to the test, when you have the time to check your answer, you should always be doing that. It's an easy way to guarantee that you're going to get your full points for getting an equation right. So for the rest of these, you're really just doing that. If your base is already the same, you're just going to set them equal to each other for the exponents, and then solve. I was using blue before. Let's switch that back. There we go. So here my base is 6. 1 is the exponent on the left side. 2x minus 3 is the expression on the right. If I set those equal to each other and solve, I'm going to add 3 on both sides first. That gives me 4 equals 2x. I divide by 2, and I get that x is positive 2. Right. With this last one in box 2, we've got 10 to the 3x power equals 10 to the 2x plus 3 power. So once again, I'm just going to start with setting those two exponents equal to each other. 3x equals 2x plus 3. It's a little more complicated because we have x on both sides of my equations, but we should still be able to handle this no problem. I'm going to subtract 2x on both sides. X equals 3. Okay, moving right along. For box number 3, now we have bases that are not the same as each other. So we've got different bases, unlike bases that we're dealing with. And with this, we still want to try and use the same property. The property tells me that if I have my bases that are the same, then I can just set their exponents equal to each other. So what we have to do here is a little bit of thinking. We have to try and get both sides to have the same base. So usually there's going to be one side that stays the same and one side that changes into another. And you have to look at what common factors they have. So here, 5, there's no way that I can simplify that down any further. 5 is a prime number, so I'm not going to be able to work with that left side. So what I'm going to try and do instead is take this 125 and rewrite it so that it is a base of 5. So we have to try and figure out 5 to what power is going to give me 125. So you can use your calculator to just play around with the different exponents of your base that you're looking at. Other than that, it's a kind of either a guess and check thing, or if you're good with your exponent rules, or if you're good with your powers, or just knowing your multiplications, then that's really kind of what it comes down to with trying to find what that number is. In this case, 125 is 5 to the 3rd power, because 5 times 5 is 25, times another 5 is 125. So that tells me right away x is just positive 3, without having to do a whole lot of thinking past that initial getting my bases to be the same. Because once I do that, again, I'm just setting those two exponents equal to each other. With number 5, I've got 4 as my base on the left side, 2 is my base on the right side. Again, my 2 is the one that can't simplify any further. It's a prime number. Nothing multiplies to get that number besides itself and 1. So I'm going to have to rewrite my 4 as a base of 2. So for most of us, that is easy enough to see that 2 squared is 4. Now the tricky part here is my base is being changed, but it already had an exponent on it. So I have to be careful here because I have just my 4, that I'm going to draw in parentheses right now. This 4 I'm rewriting as 2 squared, but it already had the exponent of x on it. So now I have to know my exponent rules. This is where what we talked about back in 6.1, I think it was. Our exponent rule for power, we have power being raised to another power, tells me I multiply those two bases, those two exponents. So the left side ends up being 2 to the 2x power equals 2 to the x minus 3 power. And now we have the same base, so I can just set those exponents equal to each other. 2x equals x minus 3. I subtract x on both sides, and I get negative 3. So a little more complicated in this case, because I had an x in my exponent that I had to deal with. But again, the name of the game is getting my bases to be the same. Didn't mean for that to rhyme so much. It happens. All right, with the last one in box 3. For this one, it is even more complicated because 9 and 27 could both simplify. And unfortunately, 27 is not a perfect power of 9, so I can't just rewrite 27 as like 9 squared. That would be 81. So what I have to do in this case, I have to rewrite both sides so that they are both the same base. Hopefully what we recognize here is that 9 and 27 are both multiples of 3. So what I'm going to do is rewrite them both so that they're base 3. Again, hopefully that makes sense for us because both of them, again, are multiples of 3. So I'm going to try and rewrite them as just 3 to some power. So we all know that 3 squared is 9, and that's still being raised to the x plus 2 power. We probably don't, most of us don't know off the top of our head that 3 cubed, 3 to the 3rd power, is 27, but we could figure it out relatively quickly. We would just take our calculator and just start multiplying by 3s, or raising 3 to different exponent powers, until we hit 27, which in this case, again, 3 to the 3rd power is 27. So now that I have them both as the same base, I'm going to simplify their exponents first and then set them equal to each other. So here my exponent rules, again, I use my power rule because I have an exponent being raised to another exponent power. So I have to multiply my exponents. So on the right side, which is the easier one, I just multiply 3 times x. On the left side, I have to multiply 2 times x plus 2. Now you have to be careful here because it's not just going to be 2x plus 2. This 2 has to get multiplied, has to get distributed into both of my two terms inside or within my exponent, because I'm multiplying 2 times that whole expression of 2x plus 2. So I actually end up with 2x plus 4 as my exponent on the left side. From here, now I'm just going to take those two exponents, set them equal to each other. 2x plus 4 equals 3x. So in this case, I'm going to actually subtract, I don't like that, subtract my 2x on both sides, and I get 4 equals x. Definitely more complicated than the others, but still the same process. I'm still making sure my bases are the same, setting their exponents equal to each other, and solve. With box 4, there's only 2 problems in box 4. With this one, we're looking at how we would handle something when your base is between 0 and 1. Now, I specified between 0 and 1 because it's necessarily just less than 1. Again, this is kind of going back to those exponential decay problems where our base is between 0 and 1, which we see is usually a fraction, but specifically between 0 and 1. So it's actually very, very similar to box 3. We're going to try and rewrite them in terms of the same bases. It's just that when we're dealing with a fraction or a number that's between 0 and 1, which again looks like a fraction, I have to make sure I remember that my negative rules, my negative exponents, flip my fractions over into whole numbers. So remember, for these, if I have 1/2, I could rewrite 1/2 as 2 to the negative first power. Because 2 to the negative first, again, I could flip that, make the exponent positive, and now it's 1/2. So going backwards, 1/2 becomes 2 to the negative first power. And that to the x power. That x is still there. So looking at that, I have my base is positive 2, which I'm going to rewrite my right side as a base of 2 as well. 4 is 2 squared. So from here, it's the same. I mean, once you have that negative exponent, once you remember that that's the case, it is identical to box 3. I'm just rewriting both sides so that they have the same base, and then setting the exponents equal to each other and solving. So on the left side, when I do my power rule, I get 2 to the negative x power equals 2 squared, which means negative x equals 2. So either multiply or divide by a -1, pending your philosophical beliefs, and you should get -2 for your x value. -2 for your x value. All right, for the very last one, for number 8, we've got 4 to the x plus 1 power equals 1 over 64 on the right side. So you've got a couple of different options on this one. You could actually do this problem with leaving the left side as it is. I know in the past we have rewritten 4 as 2 squared, which is an option for you. But 64 is actually 4 to the third power. 4 times 4 is 16, times another 4 is 64. So what I can do is on the right side here, I can rewrite 1 over 64 as 4 to the negative third power. Because again here, 4 cubed is 64. So if I made that 3 a negative, it would flip my fraction over. 64 becomes 1 over 64. Or 1 over 4 to the third power. So that's why I'm doing this. The left side stays the same. 4 to the x plus 1. Now I just, same thing I've been doing, set my exponents equal to each other. X plus 1 equals -3. I subtract 1, and I get x equals -4. So hopefully that helps. If you need to, take a second and go back and rewatch the video, or go back and just rewatch certain boxes from the notes today. Tomorrow will be a practice day on this, so you'll have some time at the beginning of class. We'll check both sets of homework. So the 6.5 practice A that was your homework due today, and then the homework that I'm writing right now, page 329, 4 through 20 evens, will be your homework tonight. So at the beginning of class tomorrow, we'll go through and check both of those. We'll have time to ask and kind of dissect all the questions you may have. And then tomorrow will be a practice day. So it can be a skill building day where we're just working on getting good at these and getting some practice with having the opportunity to talk to myself, ask me questions, all that usual good stuff. So hopefully that helps. Hopefully that went okay for you guys. And if not, feel free to watch it again. Shoot me an email if you're confused, and have a good day.